Hi, so this is Math 150, Section 1, lecture probably around 33, give or take. And so at the end of the semester, we're going to be doing TaylorSeries now, which will be a nice way to build on all we've been doing with sequences and series. I do want to start today, sadly, on a sad note, just as a way of really emphasizing why I have been doing some of the things I've been doing this semester to just drive home to you about how important it is for you to always be checking things and to be aware of what's going on and not to lose opportunities. So the original example I was going to use was the chemistry major at Yale who died because she got her hair cut in lab equipment at 2 a.m. She was working alone, forgot to put it up. Or I was going to use John Nash, who was flying back from Europe after having just won one of the biggest prizes in mathematics, $1 million, and did not buckle his seat. And there was a car accident. He and his wife died. The driver was fine. The example I will use is a 15-month-old girl, Sophia Alviro, whose mother did not realize she had forgotten to drop her off at daycare, left her in the back of the car, and she died 9 hours later. And just how easy it is to just forget things and have terrible consequences. And this is why, as you get older, as you get further in life, people are not going to be checking up on you to make sure you're doing everything you are. And that's why I just really want to hammer this home. So one of the things the poor mother is doing now, she's starting a national movement, bag and back. That when you have a little kid, leave something you need in the back of the car, so you have to go there and grab it, so you can't forget. Sadly, I teach so many students this year that almost surely one of you is going to forget something at some point when it's going to really matter. It might be bringing identification to an exam and not being able to take it and losing out. So anything you can do to just get in the habit of checking, do I have everything for whatever I need to do today? All right, so turning to mathematics now, we're going to switch and we're going to talk about Taylor series. So you've already done simple Taylor series. You've done basically the tangent line approximation, or in several dimensions, you've done the tangent plane approximation. Most of today is going to be one dimension. I'm going to show you a trick that works for most two-dimensional Taylors and 3 and higher dimensional Taylor series that for some reason people don't seem to cover. But it will allow you to cheat and calculate a lot of these very easily. So the idea is the following. You have a function f of x, and you want maybe fn of x to be a degree n polynomial to approximate f. And the hope is that the bigger degree you get, the better approximation you can do. And you have to decide, well, what do you mean by approximation? At what point? So typically you want to say in some small interval, I want to see how well do I do. And then this can become an interesting question as to how do you measure error. Maybe one polynomial does better in one region of the interval, but another one does better in another. Maybe I want to look at the sum of the squares of the errors or something like that. I'm not going to get into too much detail about all the different ways. I'm going to just look at the difference between, so h of x will be f of x minus fn of x. This is our error. And we'll just try to see what can we choose for fn and what consequences will that have on the size of the error. Typically, the more you assume about f, the better job you should be able to do. So we start off today by playing the theme song to Friends. What theorem should that remind you of? From earlier in the semester. I said, when in doubt, we always go to this theorem. It's like the Friends episode, the one with. So we use this, yes, the mean value theorem. So today is the return of the mean value theorem. When in doubt, we will be using the mean value theorem. I am not going to prove the best possible result for how small the error is. My error is actually going to be a lot smaller than what I show you, but what I show you is going to be good enough and it's going to be fairly easy to show, and I would much rather do that than do a little bit more work, have a little bit more algebra floating around, and get a result that we really don't need. So the question is, if you were to approximate a function, what pieces of information would you like? Well, we'll typically do things maybe at x equals 0, but of course you could shift to another point x equals a and just translate everything over. So the 0th order approximation is just f of 0, or more generally, it's just f of a. And what we're basically saying is, if all I know is where I start, then I will just assume for all eternity that's where I am. And if you have no other information, that's a pretty good thing to do. The next f1 of x is where I start plus my instantaneous speed times the elapsed time. Or more generally, it would be f of a plus f prime of a x minus a. And this is the time elapsed from a. So at this point, I'm going to stop writing all the stuff over here, and I'm going to just concentrate on what's going on over here. If I had a little bit more information, maybe I know my instantaneous acceleration, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared. So why do you, I had a 1 as a coefficient and 1 as a coefficient, now I have a 1/2, and I'm writing it as 2 factorial. Why do you think I have a 2 factorial down here? So I'm trying to approximate my function. Let's compute some values. What's f2 of 0? If I plug in x equals 0, what do I get for f2?
Well, it's like if you have the factorial, like continuously, the denominator continuously gets smaller and smaller, so like you're like converging to a point.
Well, but maybe the derivatives are getting larger and larger. I mean, the fact that the denominators are growing rapidly is going to help us with convergence, absolutely. What would f2 of 0 be? When I put in x equals 0, what do I get? Yeah.
F of 0.
You just get f of 0. Now let's look at f2 prime of x. So when I take the derivative, this is a constant. F prime of 0 is a constant. So the derivative of x is just 1. So I get f prime of 0 plus f double prime of 0 over 2 factorial 2 times x. What's f2 prime at 0? Yes?
F prime at 0.
So f2 prime of 0 is f prime of 0. Now I can take the second derivative, f2 double prime of x. Well, this is going to vanish. And then I have f double prime of 0 over 2 factorial 2 times 1, and the derivative of x is 1. What's f2 double prime of 0?
F double prime of 0.
F double prime of 0. And if I'd gone one further, if I had the x cubed, if I had a 3 factorial down here, when I take 3 derivatives, it will cancel out. And this is designed so that the derivatives of our approximation agree with our function at the expansion point. So fn of x will be a sum, k goes from 0 to n, of the kth derivative at 0 over k factorial times x to the k. And you can check that if I take the kth derivative at 0, I get the kth derivative at 0 if 0 less than equal to k less than equal to n. So I'm essentially using a very deterministic process. I'm looking at information at the expansion point, and I'm using that to build my polynomial approximation. This does not mean that you can't find a better approximation. But this is a really good approximation, and it's using only data that's going on at the point of interest. Okay? And the idea is that this should do a really good job of approximating your function if you're close. The further away you are, the worse the approximation could be. If you're driving a car on a highway, and you look at your speedometer, do you think you can predict where you will be a tenth of a second later? Yes. Unless there is a stopped car right in front of you that you're about to hit, you will not really have a great change in speed. Can you predict where you'll be 5 hours later? No, because you could hit traffic, you could go off to the rest area, but for a small amount of time, you should be able to figure out what you're doing. So the idea here is the more terms we take, hopefully, the better approximation this gives. We saw how useful it was to look at tangent line, straight line approximations. We can look at parabolas, cubics, quartics. The more terms you take, the harder it is to work with. Now that we have a sum, what's the first question you should ask now that you see the sum? Yes? Does it diverge or converge? And as was remarked, we have a k factorial down below. K factorial really wants to converge. And in fact, we showed that x to the k over k factorial converges for every x. This was the expansion of e to the x. So as long as the derivatives aren't growing too rapidly, we should be okay and it should converge. So the hope is that if I give you a function, the function will have a Taylor series expansion which converges and agrees with the function on an interval. So here's a nice challenge problem. Let's let g of x be e to the negative 1 divided by x squared if x is not 0, and 0 if x equals 0. I don't think I've mentioned this function before in class. Have I mentioned this one? Okay. This is one of the worst functions in all of mathematics. Functions like this should not be allowed to exist. Because functions like this exist, real analysis is an extremely difficult subject. Complex analysis is actually remarkably easy. And the reason is, for complex analysis, for a function to be differentiable, it's very similar to what we did in Calc 3. To be differentiable, the limit must exist no matter what path you take. And it turns out that forces severe restrictions on which functions are differentiable. Whereas in real analysis, you don't have that many choices. And so being differentiable in real analysis is not a strong condition. So where's the only point where it would be hard to take the derivative of g of x? 0. So you would have to go back to the definition. So g prime of 0 is the limit as h goes to 0 of e to the negative 1 over h squared minus 0 over h. Right? I'm going to let k equal 1 over h. So this is the same as the limit as k goes to infinity. 1 over h becomes k. I have e to the negative, so that comes down below, e to the k squared. What does that limit equal? So k divided by e to the k squared. What would that limit equal? 0. And you could prove this by using L'Hopital. So what this tells you is the function is differentiable at 0 and its derivative is 0. If you continue to work with a little bit of effort, it's a nice problem, you can show all of its derivatives are 0 at the origin. Every derivative is 0. Your instantaneous speed is 0. Your instantaneous acceleration is 0. The acceleration of the acceleration is 0. So if you tried to form the Taylor series, you would have all zeros. So your approximation to the function would be the function that's identically 0. So if you plot the function, it's going to be extremely flat like this. The Taylor series only converges to the function at one point, at 0. This is not impressive. Look at how we define the Taylor series. It's f of 0 plus multiples of x. You have to agree at 0. We forced you to agree. You start off as f of 0 plus things that vanish at 0. The fact that the Taylor series agrees at 0 is not remarkable. It's forced upon us. What is interesting is that's the only place where they agree. So just because the Taylor series converges does not mean it converges to your function. This just shows you how painful real analysis can be. Complex analysis does not allow something like this to happen. Real analysis is very inclusive. Any function is allowed in. Complex analysis is extremely restrictive. And it makes the subject a lot easier. All right, what I want to do now is let's calculate some Taylor series. And so we'll do a couple of examples. Then we'll do some numerics on the computer to just show you how quickly things can converge. And so, all right, let's start. So I'll call it t of x will be the sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial x to the infinite Taylor series. let's take f of x to be e to the x. What's f prime of x? E to the x. F double prime of x. E to the x. The nth derivative. E to the x. And if we then evaluate all of these at 0, what is e to the 0? 1. So this gives us t of x is the sum, and it goes from 0 to infinity, of x to the n over n factorial. So if we build the expansion, if we know that e to the x is the unique function who equals its own derivative, this is what we get. And we've already shown that this series converges for all values of x. All right. I want to note the following. Has anybody not seen I am the square root of negative 1? Okay, what would I squared be? Negative 1. I cubed. Negative I to the 4th. I to the 5th. I. So it just cycles. Okay? So I'm not going to go through all the algebra. I'll do enough to motivate it. So using our expansion for e to the x, let's look at e to the ix. This will be the sum, and it goes from 0 to infinity, of ix to the n over n factorial. Okay, I'm just plugging in I. I can formally do this. All right? Well, whenever n is even, we have I to an even power. I to an even power is going to be plus 1 or minus 1. Whenever n is odd, we have I to an odd power. It's either going to be I or minus I. So I can put the evens together and the odds together. So this will be the sum, and it goes from, I'll write n equals 2m. n goes from 0 to infinity. It'll be ix to the 2m over 2m factorial plus the odd piece. So it'll be n equals 2m plus 1. n goes from 0 to infinity. Ix to the 2m plus 1 over 2m plus 1 factorial. So over here, I have I to the 2m. So it's I squared, which is negative 1 to the m. So this is the sum, and goes from 0 to infinity, negative 1 to the m, x to the 2m over 2m factorial. Now this piece, I have an I to the 2m plus 1. I'm going to pull out an I, and then I'll be left with a an I to the 2m and an x to the 2m plus 1. So then we'll have a sum, m goes from 0 to infinity, of negative 1 to the m, x to the 2m plus 1 over 2m plus 1 factorial. So just writing this out, this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. That's the first piece. The second piece is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Okay? This is cosine of x. And this is sine of x. We could find the Taylor series of cosine and sine by doing what we did for e to the x. What do we do for e to the x? We calculated the derivatives. What's the derivative of cosine? Yes.
Negative sine.
So the derivative of cosine is negative sine. So we have cosine of x, take the derivative. We get negative sine of x, take the derivative. What do we get?
Negative cosine.
We get negative cosine of x, take the derivative. What do we get? Take the derivative again. What do we get? Cosine of x. So it's going to cycle. Now we evaluate at x equals 0. Cosine of 0 is 1. Sine of 0 is 0. Negative cosine of 0 is negative 1, 0. And you see, for cosine, the coefficients are going to be 1, 0, negative 1, 0, 1, 0, negative 1, 0. And similarly for sine. So you can prove that the Taylor series for sine and cosine are these expansions here. And this gives us what's considered often one of the most remarkable formulas in mathematics. E to the ix is cosine x plus I sine x. I believe we used this in the class earlier to prove trig formulas in like 5 minutes. You can get everything from this. Truly remarkable. Okay? It shows you a connection between the exponential function and the trig functions. And in fact, this is where the double angle formulas come from. These angle addition formulas actually come from properties of the exponential. All right, so, yes?
Okay, so when complex numbers are involved, does that sort of change how you differentiate stuff? Because
So I'm differentiating with respect to a real variable, and I have a complex variable that's just floating around for fun. So you are absolutely correct that you have to be a little bit careful as to what does this mean. And so I am playing a little bit loose with the mathematics here. What I mean by e to the I, what do I mean by e to the ix? Technically, I mean the infinite sum. And I need to be able to justify differentiating term by term. So for this situation, you've got to be a little bit careful as to exactly what you mean. I don't have a true complex variable because I don't have anything with the formula like x plus iy, where x and y are both changing. I only have one thing that's changing, but I have an I floating around for the ride. So this can be made rigorous. It's not fully complex here. It's only partly complex. Okay. Other questions on this? So I want to do the logarithm functions, and then after that I'll do some comparisons of just how well Taylor series work. So there's a couple of series that you just need to know. You should know the series expansions for sine and cosine. You should know the series expansion for the exponential function. And you should know the logarithms. Those are the big ones. You can always, of course, rederive these, but it's nice to just have a couple of them just ready. And then the other thing which I want to really emphasize is how to get new results from old. So let's start off with f of x is the log of 1 minus x. So what's f of 0? What's the log of 1? 0. So if x is a small positive number, I have the log of a number a little bit less than 1. Do you expect this to be positive or negative? If x is a little bit less, if x is positive, I have the log of a number less than 1. Do you think it's positive or negative?
Negative.
It's negative. If x were negative, I would have the log of a number a little bit greater than 1. I would expect it to be positive. So it's nice to have some sense of what you're going to get. All right, f prime of x, the derivative of log is 1 over 1 minus x. But now I have to take the derivative of 1 minus x, which gives me a negative sign. What's f prime of 0? Yes, negative 1. All right, let's take the second derivative. So I have negative 1 over 1 minus x. I take the derivative. I have 1 minus x to the negative 1. So I get 1 minus x to the negative 2. So I have a 1 minus x squared down below. I have a negative 1. I have a negative 1 coming in from the exponent of this. And I have a negative 1 from this. Perhaps a cleaner way of writing this is writing this as negative 1 minus x to the negative 1. And when I do the algebra here, I will get negative 1 minus x to the negative 2. Yes?
Why don't the negatives cancel? Do a positive. You take the derivative.
So I have a negative from here,
Yeah.
a negative from here, and then another negative from the inside. And so what's f double prime of 0 going to be? Yes? Negative 1. All right. F triple prime of x. Negative 1 minus x to the negative 3 with a negative 2 coming down, and then another negative. So I'm always going to have a negative sign over here. I'll be negative 2, 1 minus x to the negative 3. What's the third derivative going to be at 0? Negative 2. I'll do one more. About IV is as far as you really go with Roman numerals. After that, you switch to putting, a number in parentheses. So I'll have negative 2 times negative 3, 1 minus x to the negative 4 with another negative 1. So it'll be negative 2 times 3, 1 minus x to the negative 4. F triple prime of 0 will be negative 2 times 3. And what I hope you'll see is you'll have a product all the way up to 1 less than this. So I could write this as, this is negative 4 factorial over 4. This is negative 3 factorial over 3. This is negative 2 factorial over 2. This is negative 1 factorial over 1. And for the next one, I'll have a 4 that comes down, and this will go up to a 5. So you should really prove this by induction. So I'll leave that as a nice problem for you to just show that the nth derivative, this is the fourth derivative here, that the nth derivative at 0 is negative n factorial over n. All right, now that we have that, we can feed this into our formula. So the Taylor series is the sum, n goes from 0 to infinity, the nth derivative at 0 divided by n factorial times x to the n. All right, well, f of 0 is 0. So the first thing that I really care about is n equals 1. So I'll have a sum, n goes from 1 to infinity. My nth derivative is negative n factorial divided by n, and I divide by n factorial. Hopefully it's now clear why I wanted to write these like this. I had a feeling where this lecture was going. Times x to the n. What's n factorial divided by n factorial? It's just 1 over n. So we get that this is just the sum, n goes from 1 to infinity, of negative 1 over n x to the n, or a negative sum, n goes from 1 to infinity, x to the n over n, or negative x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And that's the expansion for the log of 1 minus x. Okay? This is a really nice formula to know. This is a new type of series for us. And so the question is, where does this series converge? What scares you about the series? Yes?
Alternating terms, like plus, minus.
Does that scare you, or does that reassure you?
Oh, well, yeah, that would reassure me.
They would reassure you because the alteration should actually help cancel. Give me a reason why this series might converge. One is that it alternates. Why else might it converge? Yes?
I'm just wondering, why is there no factorial on the bottom?
Because we have fn at 0 divided by n factorial, right? And the n factorial cancels the n factorial up there. That's why I wrote the derivatives at 0 like that, because I knew we were going to be dividing by n factorial. The formula is not the nth derivative at 0 times x to the n, but the nth derivative divided by n factorial. So if you want to use the comparison test, you want to compare this to something that either converges or diverges. There are two sequences that this looks similar to. What's one of them? Yes?
Harmonic series?
One of them is the harmonic. You at least if x is less than 1 in absolute value. And what's the other one it looks like? So if you look at the denominators, you see harmonic. If you look at the numerators, what do you see? Yes?
A geometric.
You see a geometric. So if x is less than 1, you've got a geometric series essentially in the numerator. And that should be enough to dwarf the harmonic. So if we wanted to show that it converges, if x is less than 1, it's not so bad. So if the absolute value of x is less than 1, we're okay. Well, we have the log of 1 minus x. I don't really want to take x equals 1 because that would give me the log of 0, and the log of 0 should be plus infinity. Right? So if I take x equals 1, I could have some issues. But if I take x to be less than 1, okay. So now, if I look at the nth term, an is, oh, wait a minute. These are all, I'm sorry, it's the next one that's alternating. This one is all negative signs, I'm sorry. This one is all negative signs. It's not alternating. My apologies. We will later see something that's alternating, but this one is not. Okay. So if I let an be x to the n over n, the question is, does this converge or not? Well, note that the absolute value of an is less than or equal to x to the n in absolute value. So it converges if the absolute value of x is less than 1. By comparison with the geometric series. So if the absolute value of x is less than 1, it converges with comparison of the geometric series. If x equals 1, it diverges by harmonic series. If x equals 1, diverges. And what about if x equals negative 1? Yes?
I'm pretty sure it diverges.
Okay. So let's see what would happen if x equals negative 1. I will kill the stuff over here. Yes?
Don't you already have a negative sign outside, or do you?
Oh, sorry. Yes. So these should all be positive because I put out the negative sign. Yes, thank you. So these should all be positive signs because I pulled out the negative sign because every term has the negative sign. So this was the Taylor series of the log of 1 minus x. We could go through and imagine I want to calculate the Taylor series of the log of 1 plus x. All I have to do is put a plus sign here and do all the calculations. But I'm going to show you a quick trick. Okay? We want g of x is the log of 1 plus x. Right? We know the log of 1 minus u. This is just the sum, and goes from 1 to infinity, x to the n over n with a negative sign out front. How can I use this to get the log of 1 plus x? What should I take u to be? So I've got the log of 1 minus, oh, sorry, this is u to the n. The log of 1 minus u is negative sum u to the n over n. I want the log of 1 plus x, yes?
Negative x.
Yeah. Just take u equals negative x. And now you get the log of 1 plus x is negative the sum, and goes from 1 to infinity, of negative x to the n over n. So this is going to become x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So by knowing the expansion of the log of 1 minus x, we can cheat and get the expansion of the log of 1 plus x in one line. We don't have to go through the same algebra. So this is an incredibly powerful technique. And I'm going to show you how to use this to do some multivariable Taylor series. So now the question is, what would happen if we put in x equals 1 here? We would have 1 minus a half plus a third minus a fourth. What do we get if we put in 1 over here on this side? If x equals 1, we get the log of 2. So the question is, does the log of 2 equal 1 minus 1/2 plus a third minus a fourth? And the answer is yes. This is an alternating series. So we never did this one. This is the last one which we haven't done. Alternating series converge so long as each term is smaller in absolute value than the previous. So we will isolate that. And this gives us a series expansion for the log of 2. So alternating series test. So if an alternates positive negative, if the absolute value of an is always greater than or equal to the absolute value of an plus 1, then the sum of an converges. And here's a quick proof. So let's say we have, a0 minus a1 plus a2 minus a3 plus a4. So I'm going to put in the absolute values, so I'm going to just assume my alternation is going like this. Because a1 is larger in absolute value than a2, negative a1 plus a2 is negative, right? And similarly, negative a3 plus a4 is negative. So this whole sum has to be smaller, or at least no larger than a0 in absolute value. But if I looked at it the other way, if I looked at a0 minus a1, a2 minus a3 is positive, and a4 minus a5 is positive. So the whole sum is greater than a0 minus a1 in absolute value. And so by looking at it this way, you can see that it will converge. So this is the last of our tests. So the harmonic series diverges, but the alternating harmonic series will converge. All right. So this will sadly almost surely not show up on the recording. So, all right. So here is the function. And what I've done is I've written a Mathematica program. I've used the manipulate key so I can actually change things. So what C does is it's a scale. It allows me to zoom in or zoom out. N tells me how many terms in the Taylor series I want to use. Right now I'm using just the first term. And x0 is what point I'm expanding about. So I'm doing a first order Taylor series expansion of the cosine function at x equals 0. So the Taylor series is 1 minus x squared over 2 factorial. So the first order Taylor series expansion is just 1. And you can see how good of a job it does. Impressive or not too impressive? Not that impressive, right? But let's zoom in. If you zoom in, at first it doesn't look that great, but then when you see what the scale of the axis is, this is 1, and this is going down to 0.9985. So it's really not changing by that much. But of course, and we're not moving by a huge amount, but you want to compare how much are you moving here versus how much are you changing here. And we're changing a lot less. And the reason is the error is of size x squared. So it's not doing a bad job. But again, it's only one term. So I will zoom out a little bit. I'll change the starting point. And you can see how good of a fit it is. And I'll zoom in. And there, you can see it's doing a really good job. And the reason is, for the cosine function, it's missing the linear term at x equals 0. It's really looking like a parabola. Among any other point, there will be the linear term, and this is why we're seeing such a terrific fit. All right, let's go back to x equals 0. And I'm going to increase the number of terms. So now taking two terms. Good fit or not a good fit?
Pretty good fit.
I think that's a pretty good fit. I mean, going all the way up to 1, it's not missing by a huge amount. And we're approximating cosine with 1 minus x squared over 2 factorial. Now, eventually it becomes a horrible fit because this is a parabola going off to infinity, whereas over here this is going to swing back up. All right, let's go to 3 terms. Oh, sorry. It doesn't want to let me do 3 terms. There was no change when I went to 3 terms. Why is there no change when I went to 3 terms? My fit didn't get any better. Yes?
The third derivative of cosine of x is 0.
The
Right?
third derivative is 0. And so because the third derivative is 0, we're adding 0 times x cubed, so we're not getting any help. So we've really got to go up to the 4th term. And now you can see the fit is pretty good. I'll zoom out a little bit. I'll go up to 6 terms, 8 terms, 10 terms. Let's go up to 12 terms. With 12 terms, we are essentially almost perfectly fitting it through an entire cycle. Right? This should drive home the power of Taylor series. With just 12 terms, and half of them are even 0, we're getting a phenomenal fit. So in terms of the computational complexity of cosine, I can replace it with a polynomial degree 12, and there's very little loss. When we were talking about how you stream information and how you just send a few coefficients and then your computer can piece it together, that's what's going on. I don't have to evaluate my function at 1,000 different points to send a really precise image of the function. I can just send you 12 Taylor coefficients, and then you can reproduce it. Okay? So this is, to me, one of the high points of Calc 3, is I don't have to send all those points. And in fact, if I want to gain more accuracy, rather than sending the values of my function at more points, just send more Taylor coefficients. You know, if I go up to 20, I guess I'm at 27 right now. No. I'm fitting cosine all the way up to essentially plus or minus 10. Okay. So for the last few minutes, I want to show you a quick trick for several variables. So I have not proven why the error is small. What do you think is the main technique for proving why the error is small? What video did I play? It's the mean value theorem. That's what you need to do to show that things are small. So we'll probably do that in class on Monday, but I want to just really do some examples right now. So we have not really defined what it should be if you have several variables. You know, the several variable Taylor series expansion is a bit involved, but here's a nice trick. So if I give you the cosine of xy, and I want to expand that, it's going to involve partial derivatives with respect to x, partial derivatives with respect to y, and different weights in front of them. But you know what the cosine of u is. What's the Taylor series of cosine of u? Yes?
1 minus u squared over 2 factorial minus u
Your plus.
plus u to the 4th.
Yep.
4 factorial.
Excellent. So what should we take u to be? xy. So if you take u to be xy, you get the cosine of xy is 1 minus x squared y squared over 2 factorial plus x to the fourth y to the fourth over 4 factorial. So in a lot of situations, you can actually calculate the Taylor series of a function of several variables if you know the Taylor series in one variable. And you can ask, I want the degree 2 Taylor series. So the degree 2 means you have terms that are of degree at most 2. What's the degree of this term? 4. What's the degree of this term? 8. So this would be the degree 8 Taylor series expansion. It would be all terms up to degree 8. Okay? Let me give you a slightly harder one. Cosine of x plus y squared. So again, we know the cosine of u is 1 minus u squared over 2 factorial plus u to the fourth over 4 factorial. So what should we take u to be? X plus y squared. And now we would get the cosine of x plus y squared is 1 minus x plus y squared over 2 factorial plus x plus y, so x plus y squared to the fourth over 4 factorial. Let's say I want the degree 4 Taylor series expansion. So I only want terms up to degree 4. Do I have to worry about the next term? No, because I've got an x and a y squared. Anything in that would be at least a degree 6. When I look at this, I have an x and a y squared. X is degree 1, y squared that's degree 2. When I square it, I'm going to get an x squared, a 2xy squared, that's going to be degree 3, and a y squared squared, that's degree 4. So unfortunately now this contributes both a degree 2, a degree 3, and a degree 4 term. So if I want just a degree 4, it would be 1 minus x squared plus 2xy squared plus y to the fourth over 2. Now when I expand this one, I've got x to the fourth, and then I'm going to have 4x cubed y squared. Do I have to worry about the x cubed y squared? Why not? It's past 4. So I would be able to stop it at x to the fourth over 4 factorial. That would be the degree 4 expansion. The other terms, the 4x cubed y squared, the 6x squared y to the fourth, they're all going to be of higher degree. So this is a way to expand functions of several variables if you happen to know functions of one variable. Just say, all right, let me use a different letter. I'll call it u. I know what cosine of u is. And now if I give you cosine of x plus y squared, I can skip all those partial derivatives. I don't have to do any of that crap. Okay? You're basically reducing to a case you already know. You're being mathematically lazy. All right. So the plan for the rest of the semester, Wednesday, we're going to do a fun application of sequences and series that will review a lot of the stuff we've been doing throughout the semester. Unlike elementary school where I'm not allowed to bring in food, I will bring in M&Ms because M&Ms are crucial in understanding the sequences and series. Friday, I'm going to try to leave as a review class. So we'll do the SES blue sheets, and then I'll just use it for whatever questions you have about the semester. Monday, we will finish up Taylor series, talk a little bit about error terms, and talk a little bit more formally about what you do in several variables. I don't think that will take the entire class. If there's specific things you want to see, let me know. I will be in Mission for lunch today from noonish to 1ish, a little bit after that. I will be in my office from 2 to 3. I will probably be in later in the afternoon as well doing paperwork. So if people do have questions, those will be good times to come. All right.